And well, so thanks everyone to join our SAP UQ student chapter webinar today. So today we have Jeremy Chen, the technician director at Homos New Zealand. Jeremy has over 15 years experience in fire engineering design in New Zealand with a PhD in fire engineering from the University of Canterbury. Today he's going to present the SAFIR GoZone for structure fire design for large compartments. Without further ado, the virtual stage is yours, Jeremy.
All right. Well, thanks a lot, Joey, and thanks Stavros and Joey for the invitation. So yeah, just again, my name is Jeremy Chan from Holmes NZ. I got my PhD from University of Canterbury. Now I'm the technical director, working in the fire area. And the presentation today, well, SAFIR and GoZone for structure fire design for of large compartments. Some people, well, if they have been to the SIF conference, like Joey or Stavros, they probably have heard this before. I've modified the presentation a little bit just to suit the young researchers, and then this is the focus of this presentation, but also going through the entire practical side coming from consulting, instead of coming just from the research side, and just to explain how the whole process coming from being a consultant. So first we are going to talk about have a bit of background of what's going on, and then to discuss about the selection of structural fire model, how we chose the model for doing the structural fire analysis, and also how we chose the model for doing the fire assessment to assess the fire severity. And that led us into choosing GoZone. So I'll talk a little bit more about GoZone, and then we'll talk about the case study, which was the focus of this particular project. I'll show a bit of the analysis outcome, and then conclude by talking about other considerations. So as researcher from university, like people doing PhD, doing masters, the research topic is basically your focus, and we do want that to be your focus. And you probably spend all the time thinking about the particular research topic and being quite academic about this, and then you come out and think of the results coming from the research. So just basically that becomes your whole focus, and that's great for researchers. Coming into the project side, coming as consultant, the starting point is you will need to win a project for you to do work. Otherwise, you don't even have a project to work on. So to win the project, you have to advise your client how you are going to control the project within the time frame and within the budget. And to do that, you also need to go into a bit deeper into details, but not too difficult because you are talking to someone not from your field of expertise. You have to explain the design method to them, and just enough detail for people to believe in you, and then letting you go ahead and do the project. And that's when you can use your research topic, use that into the application. And after that, you have to explain the results. And that will also take time because that will need to bring back to the design method, and people who were not in your field, they will ask all sorts of questions. And even after that, you have to convey the idea, like, well, what does the result mean? How do you how do other disciplines, how can they incorporate the results into their documentations, into their drawings? So all of a sudden, the research topic become a smaller part, and if you didn't really, sometimes you may not really love your research topic, especially if you are writing the thesis at the moment. But then later, actually, that becomes the easiest part to deal with because at least you know what you're doing. And the other parts, the gray parts I'm showing on the screen, those those are actually, well, still necessary as consultant, but they are not that fun to deal with, especially if you have to you have to explain things really clearly to people who have no idea what you were talking about, and then you have to bring them up to speed. So this particular project I'm going to talk about, that's just one example, but well, that brings us a project to work on. Is a large transportation hubs. For confidentiality, I'm not going to name the building. You probably can guess later on. Well, the further I'm going through the slides, and you probably can guess what kind of building I'm talking about. So the major transport hubs usually have really large compartments. You don't fill the entire compartment with rubbish. You want to have a vast open space, and the use of each area will be well defined. So it's not going to be like a shopping center, things being moved around quite easily. The field distribution within the building will be well defined as well. And when those are the background, well, when those are the given condition, then the performance-based design become more appropriate for those kind of building. Otherwise, the conventional design method would say, well, all the steel members, if you are steel structure, all the steel members need to be fire rated to a prescriptive fire rating. It's the same in New Zealand and also in Australia. And that can be, well, even without doing more analysis, you can tell that may cause a lot of wastage, and that's not going to be the smartest way to do things. So that's how the performance-based design got brought into for structural fire engineering got brought into this project. And before we go even further into running analysis, we have to explain to some parties about like, well, what is performance-based structural fire engineering design? And some of those questions you will get asked several times, like almost like every time I'm doing a performance-based structure for engineering design, I'm getting asked those questions like, well, what about the life safety? And what if people are still waiting at the other side, well, say above the floor? And how are you going to maintain the evacuation zone boundaries? And those are the things like, well, when you are doing structural fire engineering design, we are talking about a different time in the fire development. We are talking about usually at the peak of the fully developed phase of a fire. So life safety design, well, if there's going to be evacuation, that needs to happen in the growth phase, in the incipient phase. You can't really say you are going to have the life safe, well, people are going to wait until the fire is fully developed to start evacuating, or even to wait on top of a burning floor. And the performance-based design, also in terms of reduction of fire safety system, are we going to have reduction of fire safety system? That's going to be that's not going to be true. So performance structure fire engineering design, we are not taking away the fire safety, the level of fire safety. We are just in some way, we are just reporting what may happen in a fire, what will be the structure performance in a fire. And once you become consultant, and when you don't have to do those kind of calculations all the time, like in terms of knowing what kind of deflection you're going to have, some people start to forget about there will be deflection when when the structure member is getting heated. Like there will be thermal expansion under higher temperature, and there will be weakening of the structural materials under higher temperature. And that's just pure physics. That is not something we can design out using our calculation method. So those are the things you have to explain to the say the fire service or the client or even the operators of the building, that well, when your fire is not controlled, those are the consequences you are going to accept. And the better way to deal with those things is to control your fire rather than say you're going to design your structure to the infinite end and then pile on a lot of fire protection systems. So yeah, the evacuation from a deformed floor, that is not a realistic concern. There was people asking about like, well, what if the deformation of the floor become, say, there's going to be a large gradient of the floor, and how do people on wheelchair, how do they go out and that kind of thing? Um, and one thing, well, other than that not being, well, it's easy to dismiss those kind of claims, but also you will need to find a way to explain what's going on in that kind of situation. And one thing I tend to talk about is the insulation rating. That is one thing that's quite obvious for everyone. Insulation rating, the condition for failure is the cooler side reaching 140 degrees. And 140 degrees above the ambient temperature. So we're talking about at least 160 degrees or something like that. And then when your floor is 160 degrees, you are really not supposed to stand on top of it. You really need to get out. And then that is not something for you to wait. And even if people tell you not to move, well, when it's 160 degrees, it's not going to be comfortable to stand on. So so from a few, well, you from a few examples you actually well, and from a few sources, well, those are the things you have to draw together and then bring together and then explain to fire service, to the project. Sometimes you have to explain that to other fire engineers, that, well, to remove those concerns. Otherwise, the project probably will not go ahead further. So once we've done that, then we can start looking into this project. The project is multi-story. The particular one I'm going to look at, the area of interest is on the ground floor. There is going to be a baggage storage hall. So before people travel, maybe sometimes they may have the baggage stored in that building, and that's going to be rack system. And the first floor above the baggage storage system is the first floor above the baggage storage system is going to be used for retail, food hall, circulation, and then probably lounge area, and the fire safety system for a major transportation hub. They have automatic sprinkler systems, smoke detection, smoke extraction, dedicated firefighting crew on site. The sprinkler system has dual water supply. Even though like smoke detection, smoke extraction firefighters, they have almost nothing to do with your structural performance, but you basically have to paint the entire picture. Like, well, how can people get out on time so you won't be bothered by those questions when you are doing your structure fire design later. Otherwise, the same question about how do people get out when the floor is deformed, that kind of questions will continue to pop out. And the next thing is the selection of structure fire model. From the commercial sense, we need the, well, I mean, as researchers, most of you would know, like, well, there are several models out there. There's Abacus, and then we are using SAFIR, and then there are some other models, Vulcan, for example. And you can use, well, all of them have, well, OpenSeas, all of them have different use and different complexity. And the thing is, for us to choose the structure fire model is we do want something simple, because we cannot, simple and reliable. And we don't really want to spend a lot of time to learn how to use the program and to teach peer reviewer and other parties like local authorities how to use the program. So if the program is very complicated, and then you have to justify all the relationship in the like the material time, material temperature relationship you use in every step of the in the program, that will not be too attractive to use. And then, in the other hand, you also need something that's sophisticated enough. So if it's we don't want something that's simple like a spreadsheet, or something too crude. And in this case, we want something that can that can include the decay phase and cooling phase, rather than just looking to the ISO fire. And we definitely want something that can look into localized fire and fire spread. also we need to be able to cater for different materials. For this project, it's easier because we only have steel and concrete to think about. But even steel, there are different types of steels, and then concrete you can deal with different kind of aggregates. So those are the things can influence the material temperature relationship, and then you want the program to be able to handle those differences. For people who didn't know about SAFIR, that is the program we used to teach in University of Canterbury, and it is still being taught by several universities. It was developed specifically for structural file analysis. So it's a bit different from Abacus, because Abacus you can use that for anything, and then SAFIR was the intent of having the program SAFIR was for structural file analysis. It was developed in University of Liège by Jean-Marc Franzen, and now Thomas Genet in Johns Hopkins University is continuing the development of this program. And the good thing about this program is, well, we know it's finite element analysis, and the good thing is actually it's not open source. You do have the controlled thermomechanical relationship controlled by the author of this program. So by not being open source, the downside is well, as research tool is you have this extra step of feedback to the developer saying, well, there's something you want them to fix or some new relationship you want them to add to the program. So it's not as easy to change as say Abacus or OpenSys. But if it's not that easy to manipulate the code or to change the code, it's easier to convince the peer reviewer or the local authorities to accept this, saying, well, since it's almost impossible for us to manipulate anything, then the reference paper would be still valid, like all the other validation before would be still valid for this project. And that's another thing, like easy to reference. Or there are over 30 papers on validation, over 20 papers on application. So overall, we can pull out something to show the local authorities or fire service that the project has, well, we're not being the first using this program. There are several people have done like years of validation in the background. SAFIR is capable of carrying out thermal and mechanical analysis in both 2D and 3D. So it can do like 3D analysis, like what's being shown on the screen here. And the good thing about this program is it can consider decay phase and traveling fire, localized fire, and it is easy to use and easy to review. So that's the reason behind why we chose SAFIR, and we made that decision even before the project starts. Basically, homes we tend to use SAFIR over the other programs. The next thing is to do with the file model, because using parametric file is not really the smartest way to deal with large compartment. Well, I mean, you don't really need to be like specialized in fire dynamics to appreciate that the fire in this kind of large compartment is more likely to travel around rather than having the entire compartment exposed to a uniform temperature. So how do we deal with this traveling situation, like while having the fire growing and also the decay phase? You can use FDS. Everyone knows FDS here, so not going to talk too much about this. All of us also know how, well, if you want to run something sophisticated and also for a large compartment, FDS is going to take quite a bit of time or computational time. There's another program we can use called TRAFIR for SAFIR. I'm going to talk a little bit more in the next slide, but it was developed based on the TRAFIR project. And the focus of that project was on fire spread. The good thing about that TRAFIR for SAFIR file is it is easy to use, and it was developed for structured file analysis, so it doesn't give you other information. For example, not going to spend time on calculating the species yield, that kind of things, because FDS actually will give you all those information, and for structure file analysis, I don't really need those information. The downside of SAFIR for SAFIR is it is one-dimensional file spread. So the file spread is going to be almost linear, and you have to define the file spread speed. And your compartment needs to be rectangle or square. And most of the time, that's not asking a lot. So if you are designing for an office, and it's very likely your office is going to be rectangle, and in that kind of situation, SAFIR for SAFIR is probably going to be ideal for your project. In this case, our floor is not the shape of our floor is a bit irregular, so that's causing some problem, and we are moving on to GoZone. GoZone, I'm going to talk even a bit later and even more details, and it is based on zone model, but then it's discretizing the entire compartment into several tubes in that way. And the good thing is the file spread is based on critical energy rather than a set speed defined by the user, and it can handle the irregular compartment shapes. GoZone also was developed for structured file analysis, so it will only give you the information you need for doing the structured file design, the temperature at different location, for example, and it is fast to run compared to FDS. The downside of GoZone compared to SAFIR for SAFIR is the user face is not there because it's very new, and then there's no preprocessor yet, so you do have to write the code to fit into the file, the program. The reason I'm talking about all of this is, well, the project basically happened at the right time to coincide with when the research was being carried out. So GoZone is almost like the last step of this SAFIR program, which is a big research program in Europe about traveling file. And this program started, well, definitely before 2020. 2020 was that was the final report. So 3 or 4 years before that. And started from this program on traveling file of large compartments. They did some small scale testing, large scale testing, and numerical model was developed based on that, the testing results. It also came up with some simpler calculation method. So you can use, you actually can get a spreadsheet from this SAFIR result to find out the heat flux on structural members. And SAFIR for SAFIR, I mentioned that before, is suitable for rectangle space with even distributed field load. The downside of the simple zone model is you still need to have some sense about whether you are having a traveling file or you are just having a simple file spread. The difference between having a traveling file and simple file spread is, well, the decay phase. So traveling file means where you have the ignition, the fire, well, when the fire spread to some other areas, the place with ignition should start to have reaching the decay phase, and then that means your fire is actually moving. And when you have a huge fuel load, the fire is not going to be completely consumed by the time the flame reach the other side of the room. So that's just simple fire spread. It is not traveling. It's just fire spreading. And the SAFIR spreadsheet is not suitable for just dealing with fire spreading. You do need to look into the background and see whether you have the traveling fire situation. And that was done in 2020. And then after that, so Dr. Antonio Gamba, this was his PhD research. And then he developed the GoZone, and it was published in, basically finalized in 2022. So that was the time when we start doing the structured file analysis. So the timing is actually quite important here because a lot of time you make, well, for researchers, you come up with some brilliant idea, you come up with some developed calculation method, and probably you even build a program for something you came up with, and that can wait a long time before someone adopt that into a project. And this time, I think all of us are being, well, we were being lucky that the time of this project coincide with his publication, and in some ways also helping him to say, well, someone is using his research outcome. So well, it's quite a rare situation. And for example, like SAFIR, it took ages for the project, well, for the industry to catch up to say, well, this program actually can be used in the commercial sense. You can find out more detail from that published paper. You definitely can find out more detail from his thesis. And now University of Liège is going to release this program to the general public. They are still preparing the website, but well, you actually can tell what the website will look like by going to that link. So I'll repeat this again. The compartment it's not the size, but the compartment can be irregular and it can be of different shapes. You can even have different field load distribution, for example, where my mouse is. So you can have, say, half the floor having lower field load, a bit somewhere else having a bit higher field load, and then somewhere else with really high field load. So you can play with the load distribution, and it doesn't even have to look like this such a nice shape. You can say, well, that you have some rows of storage, and you want to be very precise about where those storage areas will be. And it can consider compartment boundary conditions, for example, the wall condition, the density, conductivity, specific heat, emissivity, convective coefficient. Coming from the wall and ceiling, it can give you that. And it can also consider window breakage. So you can say, well, those are the windows around the compartment, and you want them to break it when you reach certain time to introduce more oxygen into the calculation. And each fuel cell, so I was saying before, well, the terminology here being used here is fuel cell, but it's basically just some tall cylindrical tubes, basically. And then each fuel cell is defined by the growth rate, the heat release rate per unit area, fuel load, and you can also you also need to define the height of the base of the fuel above the floor area. So those are the things you would also use in FDS, and you put that into the program here. The calculation considers fire spreads through the heat flux, the cumulative heat flux, and critical energy. So when the received heat flux reach the critical energy, it's going to ignite, and the fire is going to spread to the next cell. And so that's the radiation. Well, so it depends on the radiation from the smoke layer and also from the flame, from the fire. So it's coming, the radiation, well, the heat flux come from both the smoke layer and the fire. And then it's going to decide whether the fire is going to spread. And it's also thinking the flame is not going to be transparent. So the flame is going to stop the presence of flame is going to stop the radiation coming from elsewhere to go past the flame and affecting the neighboring cells. It's quite sophisticated in that way. There was the Locafi experiment in Liège, which was the localized fire and the flame length calculated through the modified Hess-Kestad equation. So those are the background of the program. It can change from field control to ventilation control. It's just like some other. It can it can be. It can be basically it is a zone model, and then it's similar to other zone model situation. You can control, well, it's going to consider fuel control and ventilation control. And then it will chase, basically will chase the oxygen. So the fire is going to grow, and then it's going to and it will follow where the windows are, and then it's going to be more it is going to be more, the fire is going to be more severe near the windows, and then the fuel will be consumed first near the window. That's where the black area is. Those are the windows, and then later at the other side, when you run out of oxygen, those fuel, it has been consumed, and then later on the other corner, we'll have the fire consuming the remaining fuel. Right. So from GoZone, GoZone is basically dealing with the fire dynamics, and from there it's going to give me the transfer file from to be used in SAFIR, which will deal with the thermal response and mechanical response. So the transfer file is going to give me the radiation at different intensity at different points in the space. So you tell the program that, well, you are interested in this particular space in 3D, and it's going to discretize the space and give you the radiation intensity. And from there, you can use that file into SAFIR, and you build the structure model in SAFIR, and then input that into the structural model to see how which area is going to be heated out first at what time. And what I'm showing at the corner here, that is the thermal gradient of the concrete filled circular hollow section, which is the column. And at 600 degrees here, you can see one side of the column is being heated up more than the other. I mean, the temperature gradient is not, we're talking about 36 degrees compared to 20 something degrees, but it's just showing you there is this progression of heating, and the temperature will depend of the structure element will depend on the location in relation to where the fire is. So the case study here, going back to what I was talking about for this project we got in hand, the compartment of interest is 7.5 meter high. And the overall compartment is 5,500 square meter. The storage area is at the center, the purple, that's where I'm showing that in as purple, 1380 square meter. The beams are directly connected to columns, and the ones, those beams directly connected to columns are proposed to be fire rated. The columns are concrete filled CHS, circular hollow section. Concrete filled circular hollow sections, they have pretty good inherent fire resistance. So we are not proposing to fire rate them. In the concept stage, you basically have to come up with the plan like this to show those are the members you believe need to be fire rated, and some other members you believe they can be left unprotected. And once you've done that, that helps the project team to decide whether they are going to go ahead with the project or not, because that's when they are going to go and do some pricing. And so even before running analysis, you have to be pretty precise about what you believe the final outcome may be, and then you use those into the analysis model. So I wouldn't just assume everything not fire rated and then start running the analysis, because that's most likely going to fail. You assume there are some members going to be fire rated in the first place, and then you can optimize it a bit later. This building has sprinkler system, and we in New Zealand and definitely in Australia, we usually ignore the sprinkler system to say, we have to design the structure to withstand the the case when sprinkler is completely not working. That's going to be, well, not going to help this project that much because our sprinkler system has two water supply. Well, for a major infrastructure, it has regular maintenance. It definitely has a good record of how it's going to be maintained. It's a dedicated team to do the maintenance, and it has separate valves for different areas. And we also know sprinkler system statistically, they are quite reliable. And if it's operational, it controls, well, 99% of the fire. And there will be situations when it's not operational, like, for example, people accidentally turn off the valve or you lose the water supply. And that can be negated by other means, which is why in this case, we did some research. We came up with the idea saying, well, we're definitely not going to look into a case where the fire will just completely be controlled by sprinkler because that's not going to be conservative enough. And also in that case, the fire temperature will be pretty low and not even worthwhile to do the assessment. And in this case, we are looking into the what if a sprinkler head above the fire is not working, and we check the sprinkler head has coverage area. So in this case, it is 8.5 square meter of the sprinkler spray zone. So we are saying, well, let's just assume we're going to be that unlucky, and then the sprinkler head right above the flame is not working, and you have, in that case, your fire will spread. Well, you basically non-control fire for the entire 8.5 square meter, and the rest of the area may have a bit of control coming from the sprinkler system. So going back to the description of this project, it's going 6.4 meter of storage of luggage. And in New Zealand, the verification method in New Zealand is asking for 800 megajoules per square meter per meter of storage height. So we are talking about 5,120 megajoules per, well, that is the total fuel load, but we are 5,120 megajoules per square meter. That's the fuel load at the center of where the fire is going to be. And outside of that area, we are looking into the fuel load being much lower because we are assuming this. We are reducing the fuel load to represent the case where the sprinkler is actually controlling the fire. So we are not saying the fire will only grow inside this 8.5 square meter. We are saying, well, it's going to grow more severely inside this 8.5 square meter area, but outside is going to the fire size was supposed to be a bit smaller. And the heat release rate per unit area, that is something we also did some research and found out that's a decent number for rack storage. And the growth rate 150 second, that's similar to ultra fast fire. After that, so that was talking about how we define the fire, and then the next thing is how do we define the acceptance criteria for the structural behavior? We definitely don't want runaway failure. We don't want the building to collapse. The client doesn't want that. And we also chuck in this, well, maximum deflection being less than 20% of the span length. So L over 20. This one common number coming from Eurocode. And even though there were experiments before, like Cuttington test showing the maximum deflection can be higher than that, the building was still standing, it didn't collapse. But L over 20 is a common number to show that, well, your reinforcing bars have not yielded yet, or yielded to an extent that causing the floor to fail. So we presented the acceptance criteria early in the project before we even ran the analysis, and then that got approval from all the stakeholders before we ran the analysis. And then and then we put the we did all of that GoZone, and then put the build a model, ran the model, and then we found the mid-bay deflection not reaching 20%, so that was a pass. And this is the deformation shape, kind of exaggerated, but that's the shape we have there. We also look into the sensitivity study and see, well, that was requested by the fire service here, and they want to know whether, well, it's going to make a difference if the fire came from the edge of the storage area compared to the center. And from what we found was there was not much difference, but we still had to do this step to compare the heating to the structural members. So the case study, what we have done there was showing, well, the GoZone and SAFIR can be used to predict fire spread in large compartments. And building with large compartments defined field load is, well, it is better to use performance-based structure fire design. So it gave the project a lot of saving by not protecting some of the steel members. And in terms of GoZone, just repeating the information again, it's fast to run, and it can handle different field type, different floor configurations, and it will give out the just enough information, so temperature and radiation intensity for structure fire analysis. So it's not going to give you the, say, the smoke layer or the information about the species yield. And in combination with SAFIR, it is ideal for structure fire design, in particular with concrete and steel structures. GoZone is not, so far I don't believe it's suitable for timber design because it is a zone model. It cannot really handle having both fire coming from the floor level and also from the ceiling level. So exposed timber probably is not a good idea for using GoZone. So just to recap the idea, what I presented here was explain the design method while using the research coming from Antonio Gamba and also all the other research before that, SAFIR, into this project, and then have to explain the result to the peer reviewer, to the local authority. And I didn't cover the fun part, which was, well, how to win a project. That was a lengthy discussion and involved several other people, and also how to and now the design is done, how to incorporate all the outcome to other people's documentation, for example, the architectural specification, this, and then the final details of architectural details on where you should use instrument pen compared to other fire protection system. That is ongoing and almost finished, but still ongoing. So the overall project is a lengthy process, and then the research topic, what I'm presenting here, and what appear to be most interesting to the researchers, that becomes a smaller part of the overall, in terms of the timeline, that becomes a smaller part of the overall project. And just a final remark. So, well, when you are presenting this idea of doing performance-based structure fire engineering design, you have to be very clear about what we are doing. We are not here to do wonders. We are not here to say, well, the structure is not going to deform if you or we can take away all the instrumentation panel or all the fire protections. I mean, people need to be realistic about what the building will achieve, or what this structure fire analysis will achieve after engaging us. And also, we need to be realistic about the potential consequence of a fire. So this is the fire coming from Düsseldorf airport. You can see, well, yeah, the structure is standing there, and then it is not something you can go back and wander around the next day. It will take them a really long downtime it did take them a long downtime to to clear out all the rubbish and to get rid of all the damaged equipment, the soot is going to be difficult to clean already. And clearly, for structure file analysis, we don't care about soot. That's almost like the last thing we want to care about. And if things turn a bit black, then that really is not something for us to worry about from the structure file point of view. But that is going to cause downtime. So we are not here to negate that. And people need to be realistic about having structure file engineers involved is not going to cause any difference to the outcome from having a fire. The future of the structure file engineering will be risk-based design. You can read a bit more from this FIP bulletin, performance-based file design of concrete structures. And the Professor Ruben Van Kool, he's expert in this area, and he came up with some brilliant idea about what you should be like for risk-based file design, what parameters need to be considered. It will take time for the entire industry to catch up because you have to explain all the parameters to all the stakeholders. So, so far as research tool, it has been explained well enough to researchers, but how do we convey the idea to other people who are not particularly in this field? That will take time. And so that's the final remark, like what's common sense to you as researcher, as a university student, someone who studied engineering before, someone who actually studied physics. It is not common sense to everyone. And when you explain things to other parties, you may need to go back to the most fundamental part. For example, when things get heated, it's going to expand or it's going to lose some strength. So that's common sense to us, but you still have to explain to everyone to make sure, the entire project team, all the stakeholders are on the same page. Otherwise, it will be quite difficult. They are going to create a lot of obstruction during the way of the project. So that's the end of my presentation. Happy to answer any questions.
Thanks, Jeremy, for such good presentations. I let the audience to start first, and any questions from the audience, and feel free to send your question through the chatting box or just directly unmute yourself.
I had one question about was it GoZone? My question was basically the heating condition that comes out of the model. Is that only a horizontal representation or a plan view representation of the heating conditions, or is there also an element of vertical in a sense? For instance, if we've got a reasonable sized compartment, do you discern based on does GoZone discern the difference between a fire condition at say 0.5 meters above the floor level versus maybe 0.5 meters from the ceiling level?
So you will trying to explain what's going on here, and if that's not what you were asking, just repeat the question. Sorry.
No stress.
So it is going to give you the radiation intensity in 3D, which means
Okay.
it does calculate the temperature or the radiation heat flux at different height, different space. So this is, this is the way to consider that it's going to be in the 3D space, and then talking about observation domain, because if you don't set a domain and then say you want the intensity from different space, basically it's going to discretize your entire space into several points, and then it's going to give you the radiation intensity at different points. Thinking this way is almost like, if you say you put thermocouple everywhere in FDS, it's going to even though in GoZone it's still going to run pretty pretty fast. It's not going to take too long to run the simulation, but the output file will be too big to load.
Yeah.
Yeah, but I mean, the outcome is almost the same. We can do FDS and get transfer file and put that into SAFIR, and that has been done almost like 10 years ago. And this is just another way to get this transfer file.
Okay, yeah, because I may have missed something in the presentation, but I was just looking. A lot of the files that you show in the slides were from what I took to be a plan view.
Yep. Yep.
So do you have a representation of one of those 3D views?
I don't have those loaded here.
Oh, that's fine.
Yeah. And also because those files they were more to do with the field cell, like how the file is going to spread. So it's going to say this field cell basically a cylindrical tube.
Mm.
This has the file ignited here, and then the other space, those tubes, they have no fire yet, and then the fire is going to spread like that, and then each one of them is a zone model. So you will do the balance within each tube.
Yeah, okay. And so when you set up that model in GoZone, do you, as you mentioned before, does it essentially, do you plug in your thermocouples in the required locations around your structural elements, and then it kind of gives you like an Excel output file, or how does that function work?
Right. That's a good question. So for this one, let me find the file. So for GoZone, because it's pretty fast to run, basically the whole simulation would take 2 minutes, and I can build quite a large compartment. So that's basically the entire compartment with all the beams and well, horizontal the beams and columns everywhere. So 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 that's the large compartment we put in, and then told the program to discretize the space, and then and later we say, well, the most interesting part is actually at the center here, like how it's being heated up, how is cooling. So I asked the program to give me the outcome from just that space, a small space which is a bay of structure. That's the structure bay. So I set the observation domain into a small space, and that space corresponds to a structure bay.
Okay.
Yeah.
And then you just bring that
Then
across to Saphir, and that
exactly.
represents, yeah, okay.
Exactly. Yeah. So if I mean, yeah, if I say my observation domain is somewhere like really far away from the interesting area, and then that may give me some useless result to run in SAFIR, and then it's going to give me basically no heating. So you can move the observation domain around, but of course we want the most interesting part.
Yeah.
Yeah.
Awesome. Thank you.
All right.
Thanks for the question, Daniel. Is there any other questions from the audience? I actually had a quick question on page 21. Yeah,
Okay.
so you said like you define the middle bar deflection as your criteria for failure. Have you like before you decide that, have you ever think about other criteria as a failure
Right.
criteria?
Yeah. So
Mhm.
so we a lot of time we also say, I think in this case as well, we say we will consider the strand not being more than 10% of the rebar strand is not going to be more than 10%
Mhm.
of the original length, and that's coming. I think that came from the steel standard, and also the acceleration, because in the steel standard and Eurocode, you would say after L over 30, you should start checking the deflection rate. So to make sure you don't have runaway failure. In this case, I don't remember whether this particular case has the deflection being over L over 30, but you can also tell like from here we didn't have the runaway failure. So even if we do that calculation about the acceleration rate, it wasn't going to change the final outcome.
Okay, yeah, that's that's actually what I tried to ask. Like, have you ever think about use accelerate or velocity of displacement? But you said it probably the same. Like it's not bring huge difference with the final result.
And because a lot of time when you see this kind of shape, like it's hanging there, and then that's So yes, that definitely is one of the steps we because of course when you define the acceptance criteria, you wouldn't know what was going to happen next, and then we usually throw that criteria in, and just for this presentation, not that interesting, but that is one common criteria to be used as acceptance criteria.
And they actually have one more question since we are on this page. So how's the fire protection material? Has this model simulated the fire protection layer?
Right.
Or
So for this one, we didn't go into some really sophisticated way. So we were saying they have the spray on insulation material, so it's not going to be like intumescent. Even though at the end they are using intumescent paint, but we didn't do the whole simulation about the paint swelling. And we just gave it a equivalent thickness of fire protection and gave it the common thermal properties to protect the steel.
It does considering as like through the thermal heat transfer analysis.
Yeah.
Okay.
So first we say, that was so we basically made some assumption first, saying, I'm going to before I run the analysis, I'm going to say all of my steel members going to be protected to when you reach following isofire, when you reach 60 minutes of isofire, the steel member is not going to reach more than 550 degrees. And it is quite important information, because even after you run the analysis, you need to find a way to convey this information to, say, the pen supplier, and the only way to communicate with them is to go back to isofire. So when I convey the idea of those orange line, I was saying, protect those beams to 60 minutes and to 550 degrees, and they know what kind of thickness of paint to give me. Even though, I mean, my fire was not isofire, but that's the only way to communicate. And I assume that before running the analysis. So in the model, there, you actually can, probably won't show too much, but that blue line that's protected, and these so those are different from the green one. The green one is not protected, and the gray one, those are protected. So in the model is already like saying the column didn't need protection because it's concrete filled, but
so like a primary beam has been protected, and secondary beam you left like unprotected. Okay.
I didn't run the case of leaving everything unprotected. I thought that was going to fail, so didn't even try that.
I have a direct message for the audience. It's like, will those slides be shared to the audience? I just asked usually it depends on the presenter. So we usually don't share, but if he directly contact with you, and that's fully depends on you.
Probably won't share the information here. I mean, it is recorded. The video will be shared, and then
I mean, we have a video anyway.
I've got a question as well. I mean, Zero, I kind of stole the thunder on the questions. But I've got a follow-up from what Zero was asking. So I can see, Jeremy, you have done basically an equivalent to vermiculite
Yes.
spray, like yeah. And you also applied a code back on the connections between protected and unprotected. Yep. So that
Yes.
I was gonna ask if that's a failure point, but you provided a code back. Actually the question I had was, I guess it's more like a practicality one. In Australia, when you have storage, you're usually required to have like what, 4 hours fire rating,
Yes.
and this is run for 1 hour, and you assume that the fire is gonna die out by 1 hour. I know in New Zealand the requirements for fire rating are much lower.
Hmm.
And so the question I've got is actually two parts. One is it's a storage. So do you have enough ventilation to grow to such a high heat release rate?
Hmm.
Is there enough ventilation? Maybe. And the second one is uh, how did you guys decide that the fire is going to be die out by 60 minutes, basically, or all the fuel load will be
Right.
consumed?
Yeah. Yeah. So, um, well, the fire behavior we basically could observe that from GoZone. So 60 minutes is actually just a simple way to represent this case. But if the fire, well, let's say if the fire was bigger, then
Mm,
the simulation definitely would run longer.
mm,
So for other projects we have done, we let some of the fire, because of the ventilation situation, it took ages to reach go back even to the ambient temperature. So the
mm,
decay phase is super long.
mhm,
And for those situations, you definitely need to run the entire simulation to the end.
mm.
And for this one, we 60 minutes actually is after the end of the fire, because of the um basically because of how we assume the fire was going to be like with the sprinkler system being in place. If the sprinkler system had to be completely ignored, then it's going to be quite, of course, going to be a massive fire, and then the outcome will be completely different. Um,
So
so
was it a fuel controlled like fire you assumed in this case? Uh,
it is field controlled. Yeah, we basically, the space is this is just the storage area. The overall space is much bigger than this, and then
mm.
um
Okay.
yeah, so that's why we're like, well, it can even though the overall building doesn't really have a lot of, well, window opening per se, it is a massive area that it can draw the air from elsewhere.
Oh, yeah, it's very high ceiling. I saw that.
Yeah, yeah.
Because I was looking at the curve, like the ceiling temperature that you've you had, and it was quite low at the peak as well.
It is,
It's
yeah.
like it's nearly flush over just
Um,
you
yeah.
know the te
So our temperature was around, I forgot where is that. So our temperature is around, well, it's been, so the model was thinking about the 900 degrees, which was the has something about the flame temperature. It,
mm,
yeah, and then um and this was more to do with having a lot of ventilation, which also vent out the air. So if there's more, oh well, if there's not enough ventilation and then more heat build up, the temperature
mm,
will be higher. So that was um that's actually the downside of assuming so much ventilation,
mm.
and the temperature, well, yeah, the temperature got limited because of the basically become more like a free burn situation.
Yeah, because you have yeah, it burns for a the temperature is actually lower than you would expect to see.
Yeah, 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 I agree with that. The temperature is, um, I mean, that's again, if I'm going to assume, say, two or three sprinkler head fail, and then not only a 8.5 square meter area, then the
Mm,
temperature, then the overall fire will be bigger, and then it's more likely to become ventilation controlled, and then
mm-hmm.
more,
Yep.
yeah, and the feedback coming from the boundary will influence the temperature a bit more.
And the orange curve, what is it about? Like, does the is it assuming sprinkler failure? On- the orange line, like
The
the
That one,
the
or the bar.
the one on the graph that goes up to 900 and down.
That's where you that's the temperature at the center of sprinkler failure.
Ah, okay, that's what I
Yeah.
thought.
Yeah.
And okay, I was gonna say in the model, you consider individual base, right? You don't consider a global model. It's like a local bay, and if the local bay is fine, I mean Zero knows this better than I, but I guess you're looking at the geometry of the building, which one is the weakest point.
Yeah.
So did you take all the bays as that?
So yeah, because each bay is not sure whether I had that information here, but each bay is around 10 meter, well, more than 10 meter.
Mm.
And then so the sprinkler failure zone will be just within each bay.
Okay, that's
Yeah.
okay. So it was kind of identical, like that.
Yeah. Yeah,
And
exactly.
yeah.
Yeah.
Okay, that's very. I'm just wondering how this would apply to, because with storage area, well, how would it work when you compare this to doing fire loading plus um, uh, like the what's we usually do the comparison between mechanical properties reduction
Mhm.
and fire loading case, and then you compare the two. So uh, fire loading design, so point four
Um,
reduction factor
yeah, yeah.
versus the strain that you talked earlier.
Mhm.
In this case,
Well, so the loading scenario, I suppose you are talking about the load combination.
yes, low
Point for,
combination, correct.
yeah. So we did consider that because the live load, we used the point for Q because that is that the point for Q came from being accidental.
Yes.
Yeah, but then there are quite a lot of like they are like long-term live load in some way. So
Okay.
those are the ones we still keep them there
Hmm.
as the same as dead load because you basically just cannot move them.
Hmm.
Just logically not possible. So they will in the calculation we consider dead load and then the long-term live load and then the point four Q was only used on the point four factor was only used on the say the circulation people that
Okay,
cannot load.
good. So the storage area was actually considered as dead load in a way.
Yeah, but I mean these storage areas on the ground floor. So
Okay.
yeah. So upstairs that's the retail, and then
Yeah.
yeah, yep.
Okay. Right. Okay. So, I thought it was, yeah, I think you mentioned that.
No,
Maybe I missed it.
yeah. Your the situation you are thinking about is probably more like a multi-story warehouse,
Yes. Yeah. Yeah.
which is another problem to deal with,
Hmm.
and yeah, yeah.
Okay. So yeah, right. I see what you mean. Yeah. And that was applicable to beams on the ground floor and ceiling level, basically the whole area that you've highlighted there.
Yep, yep,
Beams,
yeah.
columns.
So beams, columns, and like that, and then the beams above.
Right.
So that's what was trying to model.
Okay.
Yeah,
Awesome. Awesome. Thank you.
all good.
Thanks. Any last minute questions from the audience? Well, I mean, if you have further more questions, you can just directly send a message or like an email to Jeremy to ask more detail about this project or this methodology. So I think it's time to end today's sessions. Thanks everyone for joining, and thanks Jeremy to use his time to present
Well,
with us to share his experience on a real project, which is really interesting. And I was really surprised it's like 7:30 over there, but it still looks like daytime.
oh yeah,
Yeah, is it?
exactly.
I was worried about like, oh, that's too late for for you like present?
No, it will be like this until 10 o'clock or something. So
Oh,
yeah.
yeah. Great.
All right. Well,
thanks very much. Yeah.
thank you. Thank you very much for this opportunity, and then thanks everyone. And
Thanks everyone.
yep. All right.
See you next time.
Thank
Yep.
you. Thank
I
you,
will.
Jeremy.
Bye.
See you guys.
Yeah. Thanks again.